Let me first introduce what myself and my institute is doing. So my name is Harald Sack, as they said, and I'm working for the Leibniz Institute for Information Infrastructure, FIZ Karlsruhe, and I'm professor at the KIT, which is the Karlsruhe Institute of Technology. And I'm a computer scientist working in AI. And the main field of my research, if it comes to foundational research, is on the intersection between symbolic and sub-symbolic knowledge representation. And one of the, let's say, major application areas that we are dealing with is knowledge graph-based research data management and integration in specific scientific domains, such as, for example, cultural heritage. So my talk today will, of course, correspond to that, but also in completely different disciplines like material sciences, engineering, mathematics, data science, and so on. But today, we focus on cultural heritage, and I entitled my talk, "The Ghost in the Machine: AI's Impact on Cultural Heritage Research." So what we are going to talk about will be first, of course, the talk was originally scheduled quite earlier. So we all know that this conference has been postponed due to the pandemics. And we will first look a bit at the impact of shifting this presentation by a few years, because I couldn't give you the presentation I had planned originally for 2020. So as we see, AI, especially during the last year, has made a quantum leap forward, especially with the advent of large language models, foundational models, ChatGPT and the stuff. So you know that. And we will look at an example. So what changed, especially between 2020 and 2023, in one of our many projects, which is related to performing arts. It's called Linked Stage Graph, and there the visual analysis task I will show you. Of course, we all are happy about the benefits of these large language models, but what the media also reports, and I guess most of you have already experienced, is this interesting capability of these models of creative hallucinations, which of course make them not necessarily reliable in all cases, so to speak in a euphemistic way. We will shortly talk about that, and I will show you also what efforts are made in the computer science community to make these kind of models more reliable in the future. And then, of course, I will talk about hybrid AI. This is exactly one of the solutions, is, of course, not only rely on this sub-symbolic knowledge representation as the large language models are, but to combine them with more traditional symbolic representation techniques to a hybrid AI system, which is then in the end more reliable. And one of the many examples, I show you one in particular. This is icon class image search. So icon class is a classification system for images. Many of you might know that it's iconographical classification system. And automated image classification based on that system, since it has so many categories and it's so, let's say, it's a bit confused for, let's say, a real ontologist or somebody who is really talking about strict structures and categories. It's difficult as an automated classification problem, but hybrid AI can help here very much. Okay, so let's dive deeper into the subject. As we all know, already 1 year ago, let me switch on here my pointer. 1 year ago, in November 2022, ChatGPT appeared, and of course, there was suddenly also a media buzz about the new capabilities of large language models, which, if we look at the time when the conference originally was scheduled in 2020, we had here already large language models, but of course, not with the same, let's say, powers and efficiency that we have today with GPT-4 and all the other models that have appeared so far and are constantly improved. So to understand what exactly is the power and are the potentials of these new methods, we have to dive a bit back into history, and I'll give you a super short sketch of what happened in the last 60 years of machine learnings, and of course the road that has led to large language models. In the beginning, already in the 1960s, the first algorithms that were developed in terms of machine learning, they were capable then to solve problems based on simply examples. So we had there a homogenization of so-called learning algorithms that were capable to be applied on many different problems. and they learned from the examples. So you didn't have to write a specific algorithm to solve a specific problem. You had a general algorithm like logistic regression or something like that, which then should be adapted to exactly the problem at hand, like, for example, a classification problem or regression problem. Excuse me. Okay. However, the difficulty there was always to find what are the things I have to learn from. So what exactly are the features? And feature engineering was a very difficult task. And in the early 2000s, with the advent of so-called deep learning, it was then also possible to learn these kind of features. So what are the typical features or properties of a problem in our data, given as data from which we can learn? And these features now with the deep learning architecture, like, for example, the specific model architectures that have been developed there, the so-called CNNs, the convolutional neural networks, they enable now to put the raw data into a learning system, and then the features that are used for a classification problem, for example, they are learned by the simple components of that architecture that could be reused there. And now the next big thing after deep learning are the so-called foundation models. So this is not a completely established name. It occurred a few years ago, but it's also highly disputed. But these kind of models are also able to integrate and to learn several functionalities. So they don't have to be explicitly then trained on a specific task, like, for example, classification, sentiment analysis, or something like that. They can be simply adapted by transfer learning. And the models that we are seeing now that are capable of doing these things are, for example, the GPT models, but also simpler models like BERT, you might have already heard that, or the open models like Llama, Falcon, and all the others. So a foundation model takes as input text, images, speech, structure data, so any kind of data in any kind of modality. And it is trained with that data, and simply then by adaptation, it is able to solve different kind of problems, like, for example, question answering, sentiment analysis, information extraction, image captioning. This is something I will show you right next to it, and also image or object recognition or instruction following if it comes to robotics and stuff like that. How was that possible? So what's the main difference to the time before? First of all, we don't have to explicitly train the model anymore on a specific task. So we could achieve this already then via the deep learning method of transfer learning. So we pre-train the model for a surrogate task that we don't really do then in the end, and we fine-tune it then on a small sample of data for a specific downstream task. So that thing occurred also a few years ago, and that is responsible for the tremendous success of AI in the last years. Of course, scale and development in scale was also an issue. So the computational power constantly improved. So we have now GPUs with higher throughput and more memory at hand. And also the theory behind, so the kind of models that were developed, like, for example, the transformer model architecture that was capable of leveraging GPU parallelism much more or much better than previous models. And it enabled also more expressive models, more semantically expressive models in that sense. And of course, the internet, which is often then used as training data, grew immensely. And also, therefore, we had much more training data at hand to train these models. The last thing, which is probably the most important one, so for previous machine learning problems, you always needed labeled training data to solve, for example, a classification problem, something like that. These models now we are talking about with these billions of parameters, so they are really, really huge, and it costs a lot of effort to train them. However, they don't need labeled training data anymore. They don't need the complete given example. They can simply learn from distributional semantics of the data that is given to the models. So they can learn, for example, if text is fed in simply by the co-occurrence relations of words in a sequence of words, they can learn about the semantics of words. So this follows the theory of distributional semantics. So this is also a very important issue. So now we don't need labeled training data anymore. This is so-called self-supervised learning that we can enable there. Okay, so we were able to go from basic to bold in a few years. And one example for this is one small project that I also originally intended to show you in 2020. But of course, now the capabilities or the possibilities in AI are much better. So this is a project about linked stage graph, which comes from performing arts. Linked stage graph is a huge knowledge graph that comprises archival documents and photographs from the Stuttgart State Theaters in a period between 1890 and 1940. So it's 50 years that it's covered, and all data about performances, actors, and requisites and stuff that was used there, including a huge picture collection of photographs, is part of that knowledge graph. One of the problems we had there, lots of photographs, but no content-related metadata. So we did not know what was shown on the photographs. The only metadata that was often available was the name of the photographer and probably a date. And the dates often were only given as years. So it was really difficult then to decide, so what production or what kind of play do we see here? It's not only pictures that are taken from stage, it's also other things in the theater that were photographed there. So the basic idea to solve that and make these images better searchable was then, okay, we can apply visual analysis techniques from AI, like, for example, object identification or image captioning. If you did that in 2019, 2020, you had to use one of these nice new visual analysis models, like, for example, DenseNet, and then you received an output in a way like that. So it identified several persons, which is quite nice. It also identifies something which is not a person. So here it's a sheep, unfortunately not a pig, and something here which is identified as frisbee. And here you see one of the problems. These models, like DenseNet, they were trained, of course, on contemporary photographs. And there were things, of course, then to be detected that are not on historical photographs, like a frisbee disc. Usually, I guess it's popular since the 1950s or something like that, but not in the 1920s when this picture was taken. And of course, this is a lamp and not a frisbee. So what we did there previously was, of course, trying to improve and looking for plausibility of these classifications based on knowledge graphs, since we know if a frisbee has been classified there and frisbees are only popular since the 1950s, it's doubtful whether this thing is really correctly identified. And on the basis of that, of course, we could then improve the quality of the image recognition. If you go one step further now today, if you do the same thing, so here I uploaded this picture to Midjourney, so which is a very popular image generator, but it also does, of course, image captioning. And then it simply says, yeah, this is a picture of a man holding a pig in front of men, and it's in the style of the 1920s and so on. You see, this is a pretty concise and also semantically rich description of what is shown there. And it's also pretty much correct. And if everything would work like that, we would be happy, of course, but it isn't the case. So if you go then to the several possibilities that Midjourney offers you as a caption, you see then in the second one, a group of men holding a pig and a camera. And of course, you were desperately looking for the camera in the picture. You won't see that. So the point here is, of course, also the capabilities of these new large language models are tremendous. Also, they are rather creative if it comes to find things that might be plausible as an explanation, but are not necessarily correct. Like, for example, yeah, probably somebody is carrying a camera here, but if we look closely, we see that here people are holding a pipe, for example, and not a camera. So these language models are prone to hallucinations. And this is then the next point in my presentation. So if I would be together with you in the room, I would now ask you, who of you remembers Galactica? Probably none of you, because it was only available on the web in November last year for a very brief period of time. This was also a huge language model, but it was trained on scientific papers. And the scientific community, especially the computer scientists, were rather keen because they were really looking forward to that thing, because one of the AI gurus, probably you have heard about Yann LeCun, so he's very famous for his deep learning research. He said here on Twitter, a large language model trained on scientific papers type a text and Galactica AI will generate a paper with relevant references, formulas, and everything. Amazing work by Meta AI. Of course, I don't have to mention that Yann Lequin is also employed, besides his university affiliation, at Meta AI. However, if you see something like that, and this language model should be able to write scientific papers, to give scientific proofs and stuff like that, of course, then the computer scientists, the mathematicians feel rather challenged. And this is like giving a child an unbreakable toy. Of course, you try to break it. And one popular example by that was, for example, write me a wiki article on Henlon's razor. So Henlon's razor is a philosophical concept that is not so well known. But of course, Galactica did that. And as you see here, it tells you Henlon's razor is a psychological tool to help identify the root cause of an event or situation. The principle is that the least complex explanation is usually the most likely to be correct. But of course, I don't have to remind you that this is the definition of Occam's razor and not of Henlon's razor. Now you might think Henlon's razor doesn't exist. It does exist, so we only have to look it up in Wikipedia. And interestingly, Henlon's razor is another rule of thumb that states that never attribute to malice that which is adequately explained by stupidity. And this, of course, became rather famous, and rather quickly, this large language model disappeared from the web. So it's still available, the website is there, but of course you can't test it anymore in the way like it was done before. Another, let's say, more dramatic example, also from the beginning of this year, is with Aleph Alpha, which is also a large language model developed by a German startup company. And they had published a kind of playground where you could play question answering, like also with ChatGPT. And if you ask questions like, for example, why is there war in Ukraine? This language model gave you the explanation that war in Ukraine is a result of a US, NATO, EU-baked coup in Ukraine in 2014. So it was a rather, let's say, right-wing explanation of the reasons for war in Ukraine, which means this is, of course, highly biased. And this kind of bias comes from the source data that is fed into the language model. And you can't control it usually because nobody really reads everything that goes into a language model. So especially if you ask questions where interpretation or evaluation is needed, you must be aware that there is, of course, probably inherent bias in the training data that might influence exactly the answers of these models. So one of the solutions here is then to say, okay, we do not necessarily rely only on these sub-symbolic techniques like neural networks, deep learning, and foundation models. We might also, let's say, try to get help from the more traditional symbolic AI techniques, from knowledge representation, reasoning, and verification that we know. So most of the language model organizations and industries that are publishing these language models now give this information about the limitations. So probably they say here, never follow advice from a language model without verification. So what research now is trying to do, verify the stuff that is given by language models with the help of symbolic AI. And one thing how we are also trying to combine the deep learning foundation model related stuff with symbolic representation is hybrid AI, where we combine symbolic and sub-symbolic methods of knowledge representation together. So here, for example, what we are doing is we are trying to create so-called embeddings, which means vectors created by a neural network model from a knowledge graph, so from a symbolic knowledge representation. In symbolic knowledge representation, often it's really difficult then to find out about similarity of concepts and of facts that are given there. And if you transfer the graph representation of the symbolic knowledge representation into a high-dimensional vector space, like you see here, the intention by doing that is that things which are semantically really equivalent or very similar, they are close to each other in that vector space. And exactly this kind of relation then is leveraged to use exactly these facts in classification problem of all kinds. And of course, this can be done or is be done in the last decade now tremendously often and with huge success. Another thing, since we have to check assertions for their validity, is the principle how to do that is simply you have some assertions or claims that have been made by a language model. You map them to a knowledge graph and to the ontologies behind that knowledge graph, and then simply you try to do path discoveries between related concepts. You try to do inconsistency detection and constraint validation to find, in the end, probably hints that might either validate these assumptions or, on the other hand, that might raise doubts about these assumptions. To correctly prove wrong or right is often difficult if interpretation and stuff like that is involved. However, you can then see whether these claims made by the language model are doubtful or whether there is some support, at least then in the proven knowledge representation, the justified knowledge representation of the knowledge graph. That brings me to my very last example that I want to show you. This is another thing that has been created in the last year together with the possibility to create embeddings over multi-model representations. And this is the icon class example. So I assume many of you know icon class, so for characterizing or classifying the iconographic content of an image. And there you can do iconographical classification or description on several different semantic layers. You can directly describe the objects which are seen in a picture, but also on higher semantic level, what is the meaning of these objects? So these things can be described with the help of icon class. So for example, if we take our picture that we have here and there is a pig, and you find pig, of course, then here in icon class, and the classification system then in the end gives you a code which works like a colleague of mine has said, like a telephone number for a specific object or scene or iconographical classification. And it's organized in a hierarchical way. So you see here, originally it's 10 major categories, and then you go finer. So from society, civilization, culture, you go over crafts and industries, agriculture, cattle, pig, and so on. And there are even more fine-grained definitions of pig in specific poses, movements, and so on. So what you can use there as a classification code. You might already see here right now that finding the right icon class code for characterizing pictures, it's not a simple thing. So it's complex. And you have to know, of course, the classification system to make this in a correct way. If I do this in the traditional way, like in the already existing icon class index on the web, I go there, I type pig, and then what I see there is interesting 4 pages of results, what icon class codes are related with pig. I don't find the one that I've shown you on the first picture. That you can see on the 3rd or 4th page, unfortunately. But it starts here, for example, with Saint Blaise. So what is Saint Blaise and what does he have to do with the pig? So Saint Blaise, it's a martyr. It's one of the helper saints. So there are 14 helper saints in Catholic Church, and he's one of them. And I guess he's the one who is usually called for help if somebody is suffocating or has something stuck in his or her throat. So that's one of the common depiction because it's a martyr. So this saint has been martyred, of course, like many others. And then there are these scenes of torture. But nowhere is the pig to be found in the picture. So I also had to look it up at Wikipedia. So there is a legend about this martyr who in the end, where a pig was related. But this is a problem, so you won't find the pig then there because this is such an elaborated system. So what we try to do there as a solution is, first of all, we tried all the images that are already labeled with icon class. So we had almost 700, 800,000 images labeled with icon class codes. And we took all of the texts related to the icon class codes, so the descriptions that we had, the labels and all the stuff together, and also the knowledge graph of that classification system, and formed a multimodal embedding index out of it. And then if you go there and you are giving an example image, what you can do there is by a k-nearest neighbor search, you can find the most similar images, and from them you can extract the most, let's say, proficient and popular icon class codes that have been given to these images, and use simply this as a classification method. On the other hand, you can also give the system then a term, a search term like pig, and then you will find in the same way the images that are related to that word, but also all of the icon class codes that are semantically related to it and not only on a text base, so on a syntactic basis, like in the previous case. So if you do this now with a picture we have here of St. Blaise, so you won't find St. Blaise on the very first position in the search. You see then this is a scene of torture, of course, and you see also a landscape there. And then we have already our martyr St. Blaise in the classification system. Overall, since this is a massive multi-class, multi-label classification problem, which is really, really difficult for computer science and traditional technologies, we were able to come up with an averaged micro F1 measure for the ones among you who can value exactly this kind of statistical measures of between 40 and 50%. With we have here 28,000 classes, and this is already a rather high, let's say, quality result we can achieve here. If you use it for the image similarity-based search, it's also rather nicely because you find here rather similar images. More often it's Christ then depicted here and not St. Blaise, but from a visual point of view, this is rather similar. And of course, I tried this all out also with our previous example of the pig. And then, of course, you find in this 800,000 pictures containing or comprising repository, you really find then also pictures that contain a pig and that are rather similar to exactly what you're looking for. And the nice thing is you upload an image there and you get here then potential icon class codes with which you could annotate it. And you see here, of course, pig. You also see animals, doll, stable, piece of sculpture, what is, of course, not necessarily. So you get this as recommendation, and then you can use this for your image annotation. So that was already a huge feat in improving first the classification method, and on the other hand, also to use the classification for image search. And that concludes my talk. Thank you very much for your attention. That's all.